Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In today's lecture, we're continuing with our examination of stereochemistry, what we could call stereochemistry part 2. Last lecture, we took a look at isomers, structural isomers, conformational isomers, and geometric isomers. Having introduced them, we then moved on into Z nomenclature for alkenes. But geometric isomerism occurs not just in alkenes, but also in ring structures. So what we want to do is see what can occur in a ring structure that will require you to use Z nomenclature. Now if I draw a ring structure, and I'm going to draw it edge on, so you can see the stereochemistry. And let's say I put several substituents here. Okay. So we have a Br and a Cl, CH3 and a CH2, CH3. Suppose I have this molecule and I was asked to give the name including stereochemistry or absolute configuration. First thing you always do is just provide the general IUPAC name. The IUPAC name of the longest carbon chain in this case is the 4-membered carbon ring. Carbon in a ring, 4-membered ring, is a cyclobutane. We have, off of the cyclobutane, a methyl, ethyl, a bromo, and chloro. Now we could number from the methyl ethyl 1, 2, 3, or from the bromo chloro 1, 2, 3. Since chloro, bromo, ethyl, and methyl are all the same priority, in this case it doesn't matter. So you could choose any nomenclature here. I'm going to pick the bromo just for convenience sakes. 1, 2, 3. And so it looks like for substituents we have a 1 bromo, a 1 chloro, a 3-methyl, and a 3-ethyl. Now, I order by alphabetizing. Bromo comes first, then chloro, the C, then the ethyl, then the methyl. So we have, if I'm going to write out the whole name, a 1 bromo, one chloro, three ethyl, three methyl, and, as I said, a cyclobutane. Okay. Now we have to ask the question, do we have geometric isomers in this structure? Do we have geometric isomers? Now, with regards to geometric isomerism, it is required that around the double bond you have different groups off of the same carbons. In a ring structure, we look at the carbons here and here, the carbons to which the substituents are attached. If above and below the plane of the ring on one carbon, there are two different groups, an ethyl is different than a methyl. Then we look at the other carbon. If the other carbon has two different substituents, a bromo and chloro. So both the carbons with groups above and below the plane of the ring have different groups, then you can have geometric isomerism. But in this case, as in the case of alkenes, there's no simple cis-trans name that we can use, because the bromine is cis to the ethyl, but trans to the methyl. So we have to prioritize. In this case, we use rule number 1. Rule number 1 states prioritize by atomic number. Well, atomic number works well for the right-hand carbon that has the bromine and chlorine. Bromine is higher atomic number than chlorine, so it gets priority. But if we go to the left-hand carbon, Okay, the 2 carbons off of it have the same atomic number. Rule number 2 says isotopes of higher mass get priority. Well, again, we're just working with carbon. There's no difference in isotope. Rule number 3 says if the 2 atoms are tied, proceed out the chain to the first point of difference. Well, that means if I start at this carbon and I start at this carbon, the methyl only has H's off of it. The ethyl has a carbon. That carbon's higher priority than the H. So that makes the ethyl higher priority. And because of that, we see that the 2 priority groups are above the plane of the ring, that is, they're on the same side. So this gets Z. And so this is Z, 1 bromo, 1 chloral, 3 ethyl, 3 methyl cyclobutane. Okay, well there you have it. Ring structures can also use the EZ nomenclature, or EZ nomenclature, that was covered in the previous podcast, or scribblecast. What we're going to do now is shift back to conformational isomers. And we're going to review quickly what we observed for the molecule ethane. Now you may remember last time we drew a sawhorse diagram for the molecule ethane. So here is my H's attached, if you like, to a carbon. And the carbon is attached to another carbon. And I can draw it in an eclipsed conformation. So what you see here is the sawhorse diagram for eclipsed. Now what's interesting is what would one see if one put one's eye right here and looked down the carbon-carbon bond? Well, what one would see, if one could see the atoms, would be the carbon atoms. A big circle represents the frontmost carbon. And on the frontmost carbon, you'd have the H attached to its nucleus. So for the frontmost carbons, I draw the hydrogen's atoms with their bonds extending right into the center. That means they're attached to the frontmost carbon. The hydrogens in back are supposed to line up. I draw them a little off just so I can see that they're there. Okay, not quite perfectly eclipsed, but they are eclipsed. So I draw them all off. But you notice in the back carbon, the hydrogens attached to the back carbon, I only draw them to the edge of the circle. This means that those hydrogens are attached to the carbon in back. Both of these structures represent the same thing, the eclipsed conformation. Now, as I stated, this is a sawhorse diagram, the one on the left. A sawhorse diagram. The one on the right is called a Newmann projection. A Newmann projection. They both symbolize the same thing, the eclipse conformation. You need to be able to draw both for the molecule ethane. Well, as I stated earlier, we can rotate around the sigma bond. And if we do rotate around the sigma bond, we can draw a sawhorse that will represent its hydrogens such that they don't line up. In fact, this frontmost hydrogen here is halfway between those two guys. Okay, so you would see it here. Because they don't line up, this Sawhorse diagram is referred to as a staggered conformation. How would that appear in a Newmann projection? What would you see if your eyeball was here and you were looking down the carbon-carbon double bond? Well, again, you'd see the frontmost carbon. And the atoms that join up at the very center are attached to the frontmost carbon, so I'll draw them similar to what is there. The hydrogens attached to the back carbon don't cross the outer edge of the circle. Notice that. There you go. And what you see here is how the hydrogens in back, and why don't I circle the hydrogens in back just so they're clear. Circle them in red. So here's one. Here's the other. These are hydrogens attached to the back carbon. They're staggered in between the hydrogens on the frontmost carbon. Now what's interesting, if I draw these again, and I'm going to stick with Newmann projections, is what is the relative energy difference between these two positions as that central methyl group is rotating about a single bond? I mentioned earlier that there's enough energy at room temperature for this methyl group to be spinning like a propeller. Rotation about a single bond does not take a lot of energy in the molecule ethane. But is there an energy difference? Well, it turns out hydrogen atoms have electron clouds around them. They have one electron and one s orbital that's overlapping with the sp cubed orbital of the carbon. It turns out the one electron cloud in hydrogen here and the electrons here, there is a repulsive force. There is some repulsion here between them. And the closer you get these hydrogens together, the closer these hydrogens come together, the greater that repulsion. The net result of this is that when you are eclipsed, they are at their closest approach. And so in the eclipsed state, there's great repulsion, making the eclipsed state higher energy. What about the staggered state? The staggered state, however, is that state where the hydrogens are furthest apart. And the repulsion between the electron clouds around the hydrogen of the front carbon and the hydrogen of the back carbon, say these two guys, because they're farthest apart, the electron repulsion is at a minimum. Electron-electron repulsion is at a minimum here. So staggered represents a low energy state, and the eclipse represents a high energy state. Okay, so let's redraw these if we can. So I'm going to draw them once again. I'm going to draw my eclipsed. So we got H, H. And I'm going to draw a staggered conformation here. And I'm rotating the frontmost carbon. So we have eclipsed, and we have staggered. Okay. As I stated, the eclipsed is high energy. Why don't we make a graph now, if we can? And it's going to have energy along this scale. And we're going to start at 0 degrees rotation. Okay. And we're going to rotate through to 360 degrees. Going to rotate right around the sigma bond. So halfway is 180 degrees. And halfway between that is 90 degrees. Okay. So this is 270. Now, let's pretend that rotating this H right around in a complete circle, we're going to plot all the energies. We're actually going to pretend we move this H throughout. Now, as the H moves around, it's going to be passing through various degrees of angle. And we want to mark out the degrees where it's going to be eclipsed, and then the degrees where it's going to be staggered. Now we know in tetrahedral, the bond angle is 109.5. But when we draw a Newmann projection, we flattened it out. That is, going from here to here is not 3 times 109.5. We're going right around a circle. Well, circle's 360. 3 times 109.5 will be just over 327 degrees. It won't be a complete circle. That means once we've drawn a two-dimensional angle, we have flattened it out. This angle is no longer 109.5. We've actually made it 120 from H to H. So rotating from one eclipse position to another eclipse position is 120 degrees. So I'm going to mark in a different color on the scale the angles, if we can, that will lead to different positions. Now, 0, what is half of 120 degrees? Well, half of 120 is 60, so half of 90 is about 45, so that makes 60 somewhere in here. So I'm going to mark this as 60 degrees. That's okay. And then 120 will be 30 beyond that. We're going to double this. 120 is going to be about here. Okay, so 60, 120, and then we're going to hit 180. If we increase by 60, 240, will be somewhere about here. Then we're going to hit 300. A bit too big there. Say about there. And then 360. Okay. What do we hit when we move from this position, okay, this H? I'm going to change the H color. The H we're going to shift position to track the degrees is going to be the frontmost H at the top. So moving the black H through to the blue H position on the front, rotating that far, okay, to here. That's rotating 120 degrees. So we're going to go from 0 degrees, and I'm going to mark this. Let's say this is the energy of the eclipsed. Once we get to 120, we hit that same energy again. We're going to hit, roughly, another eclipsed state, and that's the energy of the eclipsed state. And every time I go 120 degrees, I hit that energy. So when it goes to here, I've gone 240. And finally, when it rotates right back to where it was, it's gone a full 360. Now, when it rotates halfway, it is to this stage. How far is that? Well, that's half of the 120 rotation. That's 60. And we're going to make that a minimum energy. So here's the 60. How far is it to the next? Well, that's 180. And the next one, well, that's 300. So now we can draw a curve representing the energy change that we get. Apologize for the quality of my curve. It's just approximate. Okay. And what you see here is a plot of energy as we rotate this H through all the conformations. So if I was to draw it beneath each structure, I could draw a small staggered here. And I don't know if I can draw this small on the screen. I'll try. May not work. We'll give it a shot though. So this staggered is this guy. Where we've rotated the starting hydrogen, it's a different color. We've rotated the starting hydrogen, which is black, from the original one up here to this position. Rotating through to the next staggered position would give me this guy. So again, I have a H, and H. And an H. So now we've rotated here. So whenever you're minimum, you're rotating through the different staggered positions that are available. And finally, the other bottom point at 300 is where we have rotated right through all of the staggered positions. That's the black one. Okay. I can draw the eclipse positions now. So let's rub some of this out and make more room. What I've drawn up here is the first one. So this structure actually corresponds to that position. And we can draw eclipsed here. Now, and if we do that, we've got H, 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 and the black hydrogen is here. So we're rotating the front methyl, and you can see as the methyl moves, it moves to the staggered, moves to the staggered position, then it moves to this position. So we're rotating around the ring. And I'm just drawing all of the eclipse structures and all the staggered. Okay, and let's draw this guy. So again, we're eclipsed. Bad drawing. Try it again. There we go. So we got this H here, H here. I'm going to rub off this H here, so it's easy to see. And now the black H is right here. Now all you do is follow the structures where the H's are going as you proceed down the chart. And you can see we hit this H, and then we hit there, and then we hit the H straight down, and then the H has moved over here. We're rotating that H through 360 degrees. One more structure to draw. There we go. And we are back to our original position when we hit 360 degrees. Rotation. So just need black. We're back. We are. Now this type of structure is, or graph of energy and degrees of rotation, where you plot the change in energy as you go from eclipsed to staggered, is referred to as conformational whoops, no room, should be an AL on the end. Conformational analysis. Conformational analysis is where you actually plot the energy with change in energies as you rotate about a carbon-carbon single bond. You plot the change in energies with degrees of rotation, and you show what structures occur at the peaks and the valleys. Now, if I was to ask you a question for this, you would not have to draw the graph. Rather, I would provide you with the graph, and you would have to draw the structures at the labeled positions. And of course, the labeled positions are going to be the peaks and valleys. This is relatively easy for a molecule like ethane. You see that the peaks and valleys are all basically the same. There is no difference between the HH interactions from, say, this position to when you're over here. Okay, there's very little difference in the repulsions. And so the magnitude of the peaks and valleys is always the same. But this won't occur if you're looking down the carbon-carbon single bond of some different molecules. What do I mean? Let's look at another molecule. Let's consider the conformational analysis of the molecule butane. And this time, when we draw Newmann projections, though, we have to tell you which carbon-carbon bond to look down. You're actually going to see different Newmann projections depending on which carbon-carbon single bond you look down. If I draw butane this way, for example, and I told you to look down the carbon-1, carbon-2 bond so that you put your eyeball here, you see what you're going to see are the 3 hydrogens sticking off the front carbon. And then off the back carbon, you're going to have 2 H's and this big ethyl group. Let's draw that little bone up. If, for example, I draw my Newmann, not a Newmann, but if I draw my butane like this, and you were to look down the carbon 1, 2 bond, The front carbon's going to have 3 hydrogens. The back carbon's going to have 2 hydrogens and an ethyl. So a Newmann, and I'm not going to draw the eclipse, I'll just draw staggered. The Newmann, okay, the Newmann for the carbon 1,2 bond of butane could look like this. And I will give you a staggered conformation. This is the Newmann projection looking down the carbon 1,2 bond. Okay. What if I was asked to look down the carbon 2,3 bond? Okay, what if I am asked to look down the carbon 2,3 bond? Well, in this case, if I'm looking down the carbon 2,3 bond, so my eyeball is here, I'm looking down this bond, the front carbon is going to have 2 hydrogens, I'll draw staggered again, and a methyl, and the back carbon is going to have a methyl, 2 hydrogens. Now, what I want you to do is compare the Newmann projections, I'm labeling A and B. Take a look at them. Looking at Newmann projections, they look quite different, don't they? But they are actually Newmann projections of the same molecule, butane. The only difference is they're different conformations. We are looking down a different carbon-carbon bond. We're maybe rotating it a little differently. But it is the same molecule. If I drew one of these Newmann projections, could you name the molecule? If you were given structure A, could you name it as a butane? How would you know? Well, what I would suggest you do if you were asked to play with structures A and B, or identify structures A and B and determine whether they're the same or not, on scrap paper, you begin writing down what you see for the structure. Let's do it for A. Okay, so for structure A, I'm going to write down on scrap paper what the Newmann actually gives us in information. And what the Newmann gives us is, off of the front carbon right here, I have a CH3. Okay? It is attached to the frontmost carbon in A. So there's my frontmost carbon. Off of the frontmost carbon, there are 2 hydrogens. Now the frontmost carbon, the blue dot, is attached to a carbon in the rear. What's off of that carbon in the rear? Well, it has an H and an H. These 2 H's, they're attached to the carbon in the rear. And a methyl is attached to a carbon in the rear. So that's a CH2 with a methyl. Ah, it's butane. See what you do? If I was doing it for structure B, I'd look at the frontmost carbon, and I'd say, oh, there's a frontmost carbon. That frontmost carbon has 3 hydrogens off of it. So there's a frontmost carbon. I'm going to put 3 hydrogens off of it. There we go. It's attached to a carbon in the rear. The carbon in the rear has 2 hydrogens. Okay, so there's the 2 hydrogens. And attached to it is a CH2CH3. So here's my CH2CH3. And lo and behold, it's butane. These 2 things are the same. So although the Newmanns make them look different, you must recognize that the molecules appear or shown to be the same when you take the time to draw them out. Now, you must remember that although these are structures of the same molecule, they are different conformational structures. In A, we're looking down the carbon 2-3 bond. In B, we're looking down the carbon 1-2 bond. Okay, so we're looking down different bonds depending on what the question asks. So if the question asks, draw a Newmann projection looking down the carbon 2-3 bond of butane, I draw something like A. If the question asks, draw a Newmann projection down the carbon 1-2 bond, I draw something that looks like B. Okay. Well, what we're going to do next is we're going to do a conformational analysis on butane looking down the carbon 2-3 bond. And we're going to start with structure A. So I'm going to redraw structure A. And for butane, so here's my regular butane, and I'm going to look down the carbon 2-3 bond. And if I draw a Newmann down the carbon 2-3 bond, starting with a staggered conformation, okay, my staggered conformation looked like this. I'll draw it a little differently this time. So I'm going to draw the CH3 right up. We're going to have an H and an H. And we're going to make the CH3s opposite each other. Okie dokie. All right. Now what I'm going to do is do a conformational analysis on this. I'm going to draw a graph where I'm going to rotate the front methyl. I'm going to rotate it through 360 degrees. I'm going to start at 0 degrees with the staggered. And then I'm going to increase this by 60 every time. So here's 60 degrees. Make it about the same distance. Here's 120 degrees. Same distance again, 180 degrees. Same distance, 240. Why am I picking these degree values? Where did these numbers come from? Recognize they're half of 120. The angle from this methyl on the front to the H on the front is 120. And when you're staggered, you move half of it. Now remember, these angles are 120, not 109.5, because we've drawn the molecule flattened out on a flat surface. Okay. And if you can't picture that, come talk to me and I'll discuss it further with you. Okay. So we're going to start with staggered. And if we remember correctly, staggered is the lowest energy. Good. So we're going to give it this energy right here. Just a frictional value. This is E, and it's increasing in this direction. Okay. Now I'm going to rotate my methyl, and let's mark the one we're going to keep our eyes on. And when I rotate it one step to get eclipsed, okay, I'm going to get a structure that's pretty high energy. So I'm going to go to 60 degrees, and when it's rotated to this position and lines up with this H, and we're going to draw that, it's going to hit higher energy, because eclipsed, we learned, is higher energy. Now, when I rotate it to where this H is, it's going to be staggered again. And that's going to come down. but it's not going to come down as much as it was originally. Why? Well, let's draw that staggered structure. So I'm leaving the back groups the same, and I'm rotating the front alkyl carbon. And my black methyl is now changed position, and it's rotated through 120. Can you guess why? The energy of this staggered would not be as low as the energy of the first staggered. Well, first thing to note is the two staggered conformations are different, aren't they? In the first staggered conformation, the methyls are opposite each other. They're as far apart as possible. But in the second conformation, the black methyl is closer to the blue methyl. Certainly not as bad as it would be if it was right lined up, but it's getting closer. Now, these methyl groups are really large, much larger than a hydrogen. And so the repulsion between two methyls is greater the closer they get together. So comparing the staggered, which keeps the big methyls apart, and the staggered, which has the two methyls closer together, produces a subtle, small energy difference, where this staggered is lower energy than the other staggered. That means, since they're different, we really should give them different names. Okay? So what can we call, let's call this A, if we can. A and B. Well, A is called staggered Anti. B is called staggered gauche, which comes from the French, which means, I believe, left, as opposed to droite. Staggered gauche. Staggered gauche is higher energy than staggered anti, but it is still further apart and lower energy than any of the eclipse structures. Let's look at the eclipse structure that would have formed in between A and B. Okay, I can do that. Well, actually, let's see if we can draw it right here. Right over top. I have to draw it a little smaller. So we're rotating the front. And so we're going to have that, an H, an H, and our CH3. And this is an H. This is an H. And over here we have our black CH3. What's interesting about this eclipse structure so this guy was saying, that's B. I'm going to call this structure C. Structure C, my first eclipse structure, the methyl is eclipsed with a hydrogen. This structure C is what forms after you've slightly rotated A. As you rotate past C, you hit structure B, another staggered state. If you continue rotating through 260 degrees, you're going to hit another eclipse state, but this time okay, so okay. This time the methyls are eclipsed, and we'll call that structure D. So that's structure D. And what's interesting is you hit that once you've rotated the black methyl 180 degrees. But structure D, because the methyls are the largest groups, the repulsive force between two eclipsed methyls is much greater than hydrogen's. The energy of that eclipse state is higher than any of the previous eclipse states. Okay. Now if we rotate past D, we get a structure very similar to B again. In fact, in all intents and purposes, it is the same conformational structure. All right. I'll draw it. We now get structure here. Now, if I called this structure E would be the same as structure B. It is staggered gauche. I have two methyls beside each other. The fact that the methyl is on the other side, energetically and structurally, it is the same as structure B. There's symmetry in this molecule. It's just flipped over, if you like. Because of this, structure B, which is staggered gauche, is reformed again. So even though it's slightly to the right, it is still structure B. So what happens is we hit this high structure, and then we go back to staggered gauche again. If we continued now, we'd eclipse the methyl with a hydrogen again. Well, eclipsed methyl hydrogen is like structure C. And then finally, we get back to the original structure A at 360 degrees, staggered anti, the lowest energy state. Now, if I join these, I end up with a curve that looks like this. And this is the type of curve that is observed in the conformational analysis of butane along the carbon 2-3 bond. What would you be asked? Well, you'd most likely be given this energy diagram, and you would most likely be asked to draw the structures at the minima and maxima. And so what you could do is you could draw just the four structures. So let's rub this one out because they're the same. That's just B again, staggered gauche. And all you'd have to do is label them. Structure A occurs here, structure B occurs here, structure C here, structure D here, structure, oops, mix them up. C is there, B is there, and B again, C again, and back to A. Which of the four structures? Note that, yes, I recognize in structure B that you've rotated the methyl further, but if you don't draw it with different colors, then it's just flipped over. It's the same structure. Right? So structure B does occur twice, structure C occurs twice, and eventually we return back to structure A. So you should be able to draw the Newmann projections. You should be able to label the conformational analysis diagram. That's the energy diagram, which I'll provide for you. And if given a Newmann projection, you should be able to name the molecule. You should be able to draw it. You should be able to determine if two Newmanns are the same thing. And be careful when drawing your Newmanns. I mean, if you get really slack and really lazy, okay, I'm going to draw this. Here we go. And so what you end up, you go blah, 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 blah. I'm going to draw this structure. And so I'm going to draw my staggered gauche. Okay. Here we go. H, 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 CH3, H. There, I've drawn my staggered gauche. Well, if you do this, if you drew something like this, when you were supposed to do a butane, what have you drawn here? What is this guy? Well, he's certainly not. I mean, look at the frontmost carbon. What do you got off the frontmost carbon? You have an H with two CH3s. And then in the back, you have a methyl. A carbon in back with three hydrogens. What's this guy? That's not butane. That's isobutane. Why is it isobutane? Because you got careless. You put a methyl off of the same front. You put two methyls off the front carbon, when one methyl was supposed to be off the front carbon, one methyl off the back. If the line crosses the curved line, then you are saying this methyl is attached to a front carbon. If the line does not cross the curved line, then it's attached to a back carbon. So make sure you don't forget this. Okay, well there you have conformational analysis. We quickly reviewed Z nomenclature for ring systems, did one example of that, and certainly you can do the homework and try more structures if you like. Conformational analysis, we looked at conformational isomers in more detail. You'll have to be able to compare conformational isomers readily. If, for example, let's try this, one last problem. Suppose I draw something like this. And then say I drew this. Okay, that, and then that would have an H. Well, are those two conformations of conformational isomers the same molecule? Well, certainly they are different conformational isomers, but are they the same molecule? Well, let's check. The front carbon here has this ethyl, so I'm going to write it here, CH3, CH2. And it's attached, the ethyl's attached to a carbon that has a CH and a methyl. This front carbon's attached to a back carbon, so that was the bond we were looking down, that has two methyls and an H, so it's a CH, two methyls. So what we were doing is we were examining a Newmann projection down this bond for this molecule. Okay, now let's do it again. What do we got? Well, the frontmost carbon is a methyl. Okay, I can do that. So here's a methyl. Boom. And off of that methyl, it is attached to a back carbon that has an H with a methyl. So that's the H in the methyl. And then it's this CH with a methyl. And then a CH2, CH3. Okay, look at those two structures. What have we got? Well, 1, 2, 3, 4, 5. Okay, 2,3-dimethylpentane, 2,3-dimethylpentane. They're the same. The difference was we were looking down different bonds. In this case, we looked down that bond. And in this case, we looked down that bond. So yes, they're different conformations. We're producing different conformational isomeric structures, different Newmann projections, but the Newmann projections of the same molecule down different bonds. Okay, so you need to be able to interconvert, to be able to go from the Newmann projection and generate the alkane condensed structural formula, or take a condensed structural formula when asked to draw a Newmann down the specific bond. You should be able to generate the Newmann. Okay, well, that's the end of another Scribblecast lecture, specifically one dealing with conformational analysis.